you can think about this as an attempt to try to see the connections between two fields, both of which are deeply tied to learning. So there is, of course, education, which is all about learning, and then there's neuroscience, also all about learning. But the phenomena that are explored in these two domains often are sufficiently different that we don't really see ways to connect one with the other. And we're trying to see if there might be at least some tenuous connections that can be discerned. So my lab focuses on the problem of plasticity. And we specifically work with children like this young boy who have been born blind. So born with cataracts that you see in the child's eyes, a condition that at least I used to think of as being associated only with advanced age. It turns out that children can also be born with cataracts, often because of maternal infections. But what we're doing is identifying these children and providing them treatment. So say at the age of 10 or 15 years, they begin to see for the first time. So it's a remarkable change, and we're trying to see how much vision can they acquire at that time. And the reason this is an interesting question to ask from the perspective of neuroscience is because of our conceptions of plasticity. So as this schematic shows, it's generally assumed that plasticity in the sensory pathways, like vision, peaks very early on in the first few months and then declines. And by the time the child is about 5 or 6 years of age, there's very little residual plasticity. So if that's the case, then such a child, if he is being treated at 10 years of age, is essentially out of luck. We might have corrected his eyes, but the brain simply doesn't have enough plasticity to make use of this visual information that it's now beginning to receive. But to our surprise, what we're finding is that even into the second decade of life, what you're seeing here are the neuroimaging maps for a 20-year-old subject. And without going into the details of exactly what we're mapping here, just at the top level, what you can see is within a matter of 4 months, so you're seeing the functional state of the brain at 2 days prior to surgery, a week, a month, and 4 months after surgery. Within 4 months of surgery, the brain is dramatically rewiring, suggesting that there is significant plasticity there. And if this video plays, it'll give you a very visual sense of just how quickly the child is able to make use. Yep. So what you're going to see here is about a 1-minute clip of a young girl by the name of Sumitra. She's 11 years old. First, you're seeing her pre-surgically, so she's blind here. But we've asked her to try to find a box of candy that we've put by the side of the hospital corridor. And it seems like a cruel thing to do, but we are documenting just how impaired her vision is at this point. She can essentially tell night from day, but no more. That's her father in the background. And next, you see her 8 days following surgery. So it's quite remarkable how much change can happen. And we also have lots of data showing that the quality of life of these children undergoes a dramatic improvement from pre to post-surgery. So clearly, plasticity is manifesting. And the question is, how are we seeing this plasticity? What is the source of this plasticity? If the initial resource of plasticity that we are born with, if that's declined to very low levels, how might we be seeing plasticity in these children? So in thinking about that question, one possibility that we are entertaining, and it may well be a crazy possibility, but the possibility is plasticity on demand. That is, instead of thinking of plasticity as a resource that simply decays with time, perhaps the brain can bring up added plasticity when the circumstances demand that it do so. So if you are immersed in a novel environment where you have a heavy load of learning the regularities, the statistics of the environment, then perhaps additional plasticity can be made available. And that's why we call it plasticity on demand. So this idea, even though it sounds kind of crazy, actually has a little bit of experimental evidence that's beginning to accumulate around it. Here's one paper that talks about this. So the immersion of an animal, or in this case humans, in novel environments seems to enhance plasticity in the parts of the brain that are concerned with learning and memory. So if there is anything to this idea that exposure to novelty can enhance plasticity in some of the crucial parts of the brain, then applying this idea to the domain of education might suggest that if we were to take conventional educational material and we were to insert some novel interstitials in that material, might that transiently at least enhance plasticity and thereby increase the uptake of information in that material. And that's why the name of this project is Enhanced Learning Through Novelty Insertion. And these two arrows are supposed to be, with the insertion of novelty, you get an enhancement of engagement. And that, along with novelty itself, perhaps are leading to an enhancement of plasticity. So our hypothesis, the experimental hypothesis we have, is that the insertion of novelty in conventional teaching material would lead to an enhancement of learning because of an underlying enhancement of plasticity. As you might imagine, it would have far-reaching consequences if we were to find any evidence to this effect. So with this, let me invite Matt to tell you about some of the experiments that he has been doing.
So in order to test the effect of novelty on learning, we inserted a variety of videos into a downloaded lecture from OpenCourseWare. The lecture was Introduction to Psychology by Professor John Gabrielli, and we inserted two different types of videos. What we're calling familiar video, which was an instructional video on how to clean your kitchen, and the novel video being a series of YouTube, an entertaining series of YouTube videos about nature, essentially. And before and after we had subjects watch this lecture, we had them take a pre-assessment with 8 multiple choice questions and a post-assessment after with another 8 multiple choice questions. And each of the post-assessment questions, I'm sorry that some of the slide is getting a little bit cut off, but each of the post-assessment questions was associated with one section in the lecture. So we can assess how they learned in response to different kinds of stimuli. And then in addition to that, we took some biosignals, ECG or electrocardiogram, like the machine you see in a hospital, and EDA, electrodermal activity, which is a measure of skin conductance. So the basic results first. So there was learning if you look at the pre-assessment and post-assessment scores, but in addition, there may also be an effect of novelty. They had, subjects in general had a higher score in the sections of the lecture that were following novel stimuli relative to the sections of the lecture that were following familiar stimuli. And this did control for the difficulty of the question in the sense that we had one group of subjects that saw the novel stimuli first and another that saw it second. So essentially, we run into one potential issue here, which is that we already know that arousal enhances learning. And what if the video itself is is causing an arousal response. So I imagined a few possible scenarios, and essentially what the plot would be is on the y-axis, performance in the questions on the assessment, and then on the x-axis would be the arousal during the section of lecture that had the content related to that question. So, and as a convention also, so blue is supposed to be novel and red familiar. So if you were to imagine that they had entirely different arousal responses due to the different types of video and a different performance on the post-assessment, we couldn't make a strong conclusion about novelty itself. But if we got a range of responses in arousal and then saw an independent effect of novelty, then we might be able to make a stronger conclusion that there was some other property of the videos other than just the arousing effect that caused the increased performance and learning. So how did we measure arousal? So we have two different types of biosignals, electrocardiogram, which we can infer from their heart rate and their heart rate variability, their level of sympathovagal balance, and from their skin conductance, we can talk about sympathetic activity, sympathetic nervous system. So this is the pipeline, essentially. The main output of our pipeline is a set of time series, which are basically indices of arousal, and we have a set of different features. So we can compare those features. This is an example of looking at the EDA peak rate slope for different sections of the experiment and ask some basic questions. So is there a difference between their arousal during the novel videos, the familiar videos, and the lecture? Definitely. We saw a significant difference there. And is there a difference due to like the first half of the lecture versus the second half of the lecture? And we didn't see a significant difference there, which is important because our groups were counterbalanced by having one group see the novel videos first and the other one seeing the familiar videos first. So again, what we hope is that we see a range of arousal responses due to these videos, and that's not really a strong part of, or a strong component of what's causing our main result. And our data right now does suggest that there may be enhanced learning from the novel videos due to some other property other than the effect of arousal itself. And a number of our arousal indices are showing this kind of result. So limitations. So we have like low statistical power and the within subject design, a high variability, so the lecture changes overall over the course of the lecture. The content is very different. And then there's very few controlled factors between the novel and familiar videos as of right now. So moving forward, some ideas that we have, well, what we have planned for the next phase is to have a higher number of subjects. So we're going to use 30 in the next version. We had 10 previously, and a higher number of questions. So previously we had 8 total questions, 1 for each section. Now we're going to try to aim more towards 80 plus questions. And then there's a whole laundry list of ideas we have for what we can do after that. So EEG and eye tracking for measuring engagement, respiration sensing as another indice of arousal, using some sort of more controlled stimulus, like, or I should say a behavioral stimulus of like familiarity or novel exploration, maybe in a virtual environment. That says long-term memory assessment. So having a long-term memory assessment is important because a lot of the previous experiments done on novelty show an effect on consolidation of long-term memory. And doing a between subject design, which will control for cross-contamination between the two halves of the experiment and a no insertion control. And we've also been playing around with the idea of doing some sort of remote experiment. If we can surpass the technological challenges and maybe have some sort of portable sensor box, we'd be able to collect a lot more data. Thank you for everyone who's contributed to this study. And if you'd like to participate, please email Annie, who is doing all of the recruitment. And also thank you, Annie, for all your help, too. You've been contributing and helping me a lot through this. So, yeah.